Yeah,
Perfect.
our first speaker is Florian from the University of Bern and in the Department of Science. He's currently a PhD student. I see from his background, he's joining us from his Huta in Matterhorn in Zermatt, and he'll be discussing what are you doing, human activity recorder. Thank you. Good to have you here, Florian. Thanks for joining on from 9 p.m. or so in Switzerland.
Yes, thank you for having me. So even though this is not my real background, I come from very close actually, and it looks like that if you look outside the window. Well, we can't because it's dark. So hello together and welcome to my presentation about what I am doing in order to find out what you are doing and to enable you to find out what others are doing. So most of you are familiar with the terms accelerometry and machine learning, I'm quite sure, and I've had experience so far that this is the case. So both of the words have become buzzwords respectively. In health science, it is accelerometry, and machine learning we talked about a lot now in the previous talks. And I noticed that in the speed networking session before that many of the present people here have extensive knowledge of machine learning, but also some of the present do not have any experience at all. So if you're interested in the specifics of the model that I'm going to introduce, then I invite you to ask me afterwards, and I shall be happy to provide you with the details. But for now, I will try to keep it simple. So as a short overview, I will present who I am, what it is that I am doing, why I am doing that, and why you should be doing the same. Also, what I will be doing in the future and I'm doing now to improve the model that I'm going to introduce. So all of the things I'm saying are gross oversimplifications. All of you are used to that. This is why you're listening to talks now, and I do not have much time, so I will keep it as short as possible. If I go to the next, yeah, now it works. So I'm a neuropsychologist, actually, and PhD student at the University of Bern. I will get you to know with all the things that I'm doing over the next few slides. I will do a lot of sports, and this is why I became interested in sports science, and then I went into health science. And I'm a sports scientist doing big data at the Institute of Health Science and University of Bern. So enough about me. What is it that I'm actually looking at? I come from neuroscience. I'm investigating the default mode network. Some of you might heard of it, some of you not. As again, a gross oversimplification, the default mode network is a large-scale brain network of different interconnected areas that oscillate with each other. They seem to be active in synchronization. If you are not focused on the outside world, so if you're at a wakeful rest while daydreaming or mind wandering or whatever, that is not task-oriented. So what I want to do is find different patterns in EEG signatures between very active and less active people in order to use this knowledge later to make people more active, which I think is the goal of many of the present people. So I want to distinguish between active and less active people for what I'm doing. So what do I use for that? I could, of course, use a questionnaire, which gives us data, not much data, and not very reliable data, also not very valid data. So I chose, of course, to do this software-based, which can be a problem, and I will go into all of those problems in the next few slides. We are interested in big data, so naturally I chose to make use of all the tools available, and I wanted to have an activity recognition software that can help me distinguish between a group of active and less active people within a larger group of people that we'll take a look at. So what should activity recognition software be able to do? It should be able to record data, to send the data to servers sporadically, so it does not get lost with battery life if the device is running out or something. It should classify the activities with some accuracy. It should do so automatically without much interaction of the researcher, of course, to minimize the work that is needed for the categorization and also to minimize the mistake potential. Privacy and security are some words that we have gotten all too familiar with in the last 2 years, especially. They should be addressed and guaranteed if possible, because we are working with patients and their data should be protected. But it is not as easy as one might think, and all of you should be familiar with that problematic as well. So automatic classification also addresses privacy concerns. because if classification is automated, of course, the researcher doesn't need to see what the subjects are doing or how often, and he cannot even see that. This way, studies can be blinded further to the point where access to raw data can be restricted for individuals having influence on outcomes and so on. Repeatability is one of the main concerns in science, and this is one of the main points why I chose to do the software myself. You will see shortly why this is the case. With the classification algorithm known, classification is repeatable, which means that if I look at a study, I can actually, reproduce the study. This seems to be obvious, but I will explain shortly why this is actually much more complicated of an issue than one might think. Privacy and security are also part of that, and you will see the connection there shortly. So one of the next points that we should address is sparsity. It's also one of the main concerns of mine. We want long battery life, so we want a very simple algorithm in sorting the different behaviors based on accelerometry, because that's what I'm doing. And we want relatively simple algorithms, so we can understand them somewhat. We touched before on that with Shapley values and so on. The last point, but not least point, is adaptivity. So I want to have a software that I can adapt later to all the research questions, that I can train on different behaviors, so to recognize future behaviors that have not been part of the initial data set that the algorithm has been trained on. So how would I explain now what all of you are asking yourselves? All of you are thinking, or I think that you might have had thought, why am I not using all those products that are available to us, to the general public or to researchers that actually are doing this already? So with the usual suspects of Fitbit, Garmin, and Samsung, and so on, and the usual suspects that are tailored more to scientific needs, like Actigraph, Movisense, and so on. I've worked with all of them in the past. I'm actually a developer at Fitbit and Garmin officially, which is not hard to become. So I had some insight, and I felt that none of the categories, like the more towards consumer electronics and more to scientific values, scientific software, those categories of devices and softwares, they do not actually fulfill the purpose, not to the extent that I want, because all the points that I showed you before that automatic recognition software should be doing, they are not guaranteed by either of them. So we have very briefly some points that we have to look at that most people are not aware of. So while many are discussing different software to recognize patterns in here in accelerometry, this is more complicated. So let's look at the disadvantages and advantages of this different software available. I just categorize it in software that is tailored towards the commercial market and to the scientific market, more or less. I know this is a very big oversimplification, but please bear with me. So our commercial software is mostly obfuscated, so we cannot actually see the source code. It is not open source, and thus we cannot actually see what the algorithm is doing or how it has been trained. In scientific software, this is mostly the case, but not always. And some sorting algorithms have actually been released by some of the products that I've shown before. Commercial software is often updated. This is one of the biggest problems. So if you look at Garmin, Fitbit, and the usual suspects, problem with them is that they update once a week or once every 2 weeks their software. And while much of this has to do with bug fixes and with security concerns, this also means that we rarely are able to revert software to a previous state. This is a problem then, because all the science that we have done previously with the previous version is then not repeatable, because again, the commercial softwares usually are obfuscated, so we cannot revert to a state that has been used in the past. So even though the security concerns are addressed, it still is a very big problem that we cannot revert to a previous state. Scientific software is rarely updated, somewhat repeatable. So for some of the companies manufacturing those devices and software, they let you use older versions, but not all of them. Commercial accelerometry does not require additional devices other than a mobile phone. I will come back to this later. But also they are, of course, tailored towards wearables. They want you to buy the wearables, which can be quite expensive. Also, the disadvantage here is that if you buy those variables, then they are not made to last for the next 10 years. Quite the contrary, they are made such that they last for 1 or 2 years, and then you would replace them, because this is actually the main selling point of consumer variables. Then, if you look at the scientific software trackers, scientific software and trackers, they additional devices, as far as I have encountered it so far. The ones I work with is Mobisense and Actigraph and so on, and they require you to have a device which is quite clunky as compared to the other devices that are available for the general consumer market designed, but both at the cost. So in commercial software, it's mostly not adaptable. You can train your old watch to recognize some behavior patterns, but this is not, again, with the combined with the point of it being up. It's a problem. I do not know how this training now I went over, and it's also just localized. So for one device only, it cannot be transmitted to other devices as far as I am aware of it. And of course, we want for all the people that we are tracking and we're doing science upon their accelerometry, we want them to have the same sorting algorithm. Otherwise, that would be a confounding variable and would be a problem then. Scientific software, as far as I have encountered it, is not adaptable. I'm sure there are some things that some of you might know, but I am not aware of them. Then privacy, the last 2 years is not guaranteed. This is a really big problem, actually. There were many big data leaks in Garmin and in Fitbit that I am aware of, and this is actually also the main reason why we don't buy them, because we are working with patients, with psychiatric hospitals and so on, and also especially with kids, which is, legally speaking, quite a big hindrance to actually So also one of the biggest points for me doing machine learning and being based in AI is that the raw data is not accessible in commercial software, like the accelerometry, all the different data points that we get, like 50 a second per dimension or so on, depending on the sampling rate. This is not available to me at all. I have tried and they would not give me access, even though I guaranteed that I will only use it for scientific purposes. Scientific software gives you access to raw data. We have one of the aforementioned devices. I will not disclose which one. They wanted us to actually pay for getting the raw data out of the sensors that we have bought from them. So yeah. So as we see now, neither of them actually gives me what I want and gives you what you should be concerned about. So I, of course, went down the way to make my own software, and this is available to the general public now. What did I do? I concluded that both categories, in which roughly I can put accelerometry devices and software, and they're too expensive, they're obfuscated mostly, not reproducible after an update, and privacy cannot be guaranteed, and they're not adaptive. So they're not very attractive to me, but to do an alternative, which is equally good, is quite hard to do. But I am a big believer, of course, in open source software, as many of the people that are here today. And I decided I'm going to make a software which is going to be part of my PhD, which will help me and hopefully help many others in circumventing all those companies that are charging for something that is not ideal for scientific purposes, in my opinion. So it should be reproducible, free, adaptive, and explainable. Yeah. So the buzzword here is machine learning. Of course, most of you are familiar with that. I've seen a great variation in experience, so I'm kind of just giving a very brief overview. You all know artificial intelligence as a wider word that has been used to describe algorithms that behaves in a way such that you could think that they would be intelligent. Machine learning is part of that, and deep learning is even a part of machine learning, which is a little bit more complicated. I'm sure most of you have touched on that. I am more into deep learning. Depends on the topic, of course. Yeah, what I'm using, what I have used for my software, the basis, of course, is deep learning, because this is the go-to approach. So very roughly, it works like that. We have different layers of neurons. They're interconnected, and this then is somewhat figuratively the algorithm. All of those neurons are interconnected between some layers, but not all of them between other layers. Some of them are recursive and have an effect on themselves. and so on. That's a very complicated topic, which is not should not be the focus here in my presentation, because all of you can look this up very easily. What we did is, at first, the go-to approach, if we have accelerometry data, and we want to conclude which behavior that led to this accelerometry data, the go-to approach would be just to make a neural network, a simple architecture, and then just put in some data, train the network, and then the output is relatively accurate. And then I can make my publication. Oh yeah, I've developed a very accurate sorting algorithm which can categorize, and many people have done this. This is not a big surprise. Also, it's problematic. And why is it problematic? So the problem here is that if I train deep neural network on data that I have, and then I test it on that data and not on other data sets, then the accuracy is quite high and it looks very well. But the problem is, of course, that we want to train an algorithm and then use it on data that it has not been exposed to before, and it should still be working. So I'm working mostly with accelerometry data that looks like that. I have different dimensional inputs. I have X, Y, Z axis. I have then the gyroscopy, which is the rotation around those axes, and a certain sampling rate. And the sampling rate, of course, if this is fixed and the dimensional input is fixed, meaning like I have always the same amount of sensors that are active, and this never breaks down for any reason whatsoever, then the input is consistent, and this is what most machine learning has been done with so far. So now, of course, I want to apply this to other data. I want to be able to recognize pattern in completely different data. How would I go about that? So I was looking into research that has been done already by people that have had great success doing so, because I myself couldn't do it. I always had the simple deep neural network architecture. I modified it heavily, of course, as we all have, or most of us. I get great accuracy, but with others, I do not. So there was a study by Malekzadeh, Clegg, Cavallaro, and Haddadi in 2020. Some of you might be familiar with it, some might not. So they proposed a new model, and they, so to speak, made a part of the software that you can include in your deep neural network architecture. Is several layers actually that interact with each other. You slide over the data in a window manner, and I invite you to look this up for yourselves, because I do not have the time here to go into details too much. So they call it a dimension adaptive pooling layer. What this means is that the dimensions of the accelerometry, they can change and it still will be accurate. So which dimensions do I have? I have X, Y, Z. I have the rotation around the axis, and sometimes I have attitude changes and others. So this then would be one side of the dimensions, and then the other side would be the sampling rate. So how much information do I get per second? Do I want a sampling rate which is 120 data points per axis per second? This gives me great accuracy, but the problem with that, of course, is that the battery life will diminish quite quickly. This will not, the battery will diminish quite quickly with the charge, and I will not be able to use this over a longer period of time. So I want to be able to have a low rate. That makes no sense, because a low sampling rate, then I have less data and then it is less accurate. So what I would want is, for example, a high sampling rate when the person is very active and a low sampling rate when the person is sitting. And to vary this, I vary the input. If I vary the input, my algorithm has to be consistent in still classifying with different. So they did fully connected layers, a recurrent network layer thing. It is quite complicated. What they did is they shuffled the input such that it does not matter what the input dimensions are, and still it will be very good at classifying still. So how did we implement this? How did we make sense of all the different dimensions, of all the different data sets? Yeah, this is straightforward. So we built an Android app which collects data. It is also available in the Google Play Store, by the way. It took me a great deal of time to actually implement this. It's called Human Activity Recorder. In the end, there will be a QR code that you can scan if you're interested to contact me about this, and then you can use it. It is Java-based, which was a pain in the you-know-what for me to do because I was not very versed in this language as I have been in other languages. So yeah, but still, we have an app that collects data. Then we collected our own data on the course of the University of Bern with hundreds of participants with my app in their pocket. Yeah, a great deal of data. Then we took the model that was proposed by Maxella et al. And we greatly modified it to the extent that it actually is much, much simpler now. We still have the adaptive layer in between, which is the bigger one. And it is a little bit wider here. We can see that. And still, it is very accurate, even on data sets that it has not been exposed to previously, which gives me great joy, actually. It took me months to perfect that. And now we're at the point where we have an algorithm that can classify very accurately, even on data that it has not been exposed to, and also with varying input dimensions. So I have the app, I have the algorithm, and we put it in a repository and commented it as far as we could, so everybody can understand it and can use it. And it is quite adaptive now and robust against different dimensions of input. So what am I doing now? I saw during the development of the app and of the algorithm that I've trained on this, on these data sets, which are the original data set, our data set, and other data sets. I saw that there are different problems. So we run into a problem that half of the population in some countries are using iPhones, or like a third of the population more likely, which poses a problem, of course. If I only have an Android app, there might be a bias in there because people would choose different devices, and I use their own devices actually to track them. So I'm redoing the app at the moment. I do it in Kiwi, which is a Python programming language, and most of us are more versed in Python than they are in Java. Java is more low level as compared to Python, and it is therefore in the common interest of the scientific community to make it easier, and this, I think, is achieved using Python. The app already contains the sorting algorithm locally, so on the device, actually, the categories can also already be identified, and the algorithm can be trained on new behaviors quite easily. And the training times are much, much less because, again, we have the architecture that is much simpler than the original architecture. This looks like a two-dimensional thing here, but it's exponentially longer actually to train. Even though we use high-performance computing to train the algorithms, it's still nice to have a simpler algorithm that locally can achieve great accuracy. So we are at the moment collecting data with kids and with elderly patients, and we are trying to implement this such that we train the algorithm on this data as well, and that each additional data set that is added to a repository can be used, and automatically it will be retrained on that, and we will look for accuracies, and they are getting better and better, but we still have a long way to go. We want to have different patients with different impairments also as well in there, and we want to train different versions of the algorithm so it actually recognizes in one stage, is the person impaired, is it an elderly patient, or is it a kid, or is it a 25-year-old sports student, and then accordingly choose the algorithm based on which it will then sort into the categories. I have left out a great many of details here, and I would be very happy to answer some questions. If you want to, if you're interested in this whole thing, then you can contact me by scanning this here, yeah, which will just direct you to my email address, and I would be happy if you would contact me and we could find a solution to answer your specific research questions. So with that, I would be at the end of my presentation and open to answer questions if we still have time.
Thanks, Flurry. Are there any questions, Ran, in the Huva app?
No, there is no question from the web page.
I have a question, if that's okay, if we have time.
Mm-hmm. Of course.
You mentioned an interesting topic of this sort of domain generalization, training to some data set and trying to extend, in particular for neural networks, trying to extend outside the data set. And then you came back to that concept a little bit. It's a related concept, but mentioning the implementation only for Android phones. So there could be a bias in the demographic. And is that, have you,
Mhm.
I know you're sort of implementing this iPhone, but I'm wondering if you have any reason to believe that that would be the case. Is it known that there's like a demographic bias between Androids versus iPhones?
No, I do not generally believe that actually, but we can only look
Okay.
into that when I have finished this app, and I can, I can then see whether there's a pattern difference or not. What I'm more afraid of is that the basic sensor works differently, because Apple has done a great deal in making their own sensors now, their own central processing units and so on. So those might greatly differ between Android phones in general and then Apple phones. This is something I'm concerned about actually more, but also there might be a bias, and I just want to be sure that I can exclude this bias.
I see, interesting. And do you find the bias also with people who download the app voluntarily versus, you know, I mean, ideally you'd like to sort of sample from an even population. And there must be some sort of bias just from a self-selection bias of people who would be willing to download the app.
Well, the biggest bias there is that, that my funding is restricted such that I have a great many sports students that downloaded the app and use that, because we developed it together. I give classes like data science classes at university. And the problem is that many people that have downloaded it are currently research subjects of mine, because I have not done any move to market this towards anybody else than scientific community so far. I'm working with different groups, and it's just the subjects mostly that download the app. So I cannot answer these questions truthfully, I think.
I see.
Right, I think thank you very much. If there are no further questions. Yeah. So we still have another speaker, the first one, Nina. I think she has some hard time to join us. We don't know whether she will join us later or not. So my recommendation will be maybe we can move to our next speaker, just in case Nina will come in and she will still have time to talk about her research. So Maryland, are you ready? Maybe you can have your presentation first. Now, yeah.
Here we go. Okay, sure. Hi everyone. My name is Marilyn Gartley, and I'm seeking my master's in computer science. I am also a lawyer. I've been a lawyer for, I guess, 13 years in affirmative complex commercial litigation, meaning that I basically collect for the benefit of the public interest, generally in the realm of securities fraud, corporate malfeasance, breaches of fiduciary duty from the board of directors or other corporate hierarchy governing entity. And in addition, I have served as a white collar prosecutor and a securities regulator. So I'm back to get my master's at 40 in computer science in order to kind of bridge the gap between the technical side and the legal side, so that we'll have beneficial regulation that will actually restrict the nefarious uses of this form of technology, while concurrently allowing for it to develop and provide the sort of benefits that we're seeing. So with that, I will share my screen, and I'll try to go as quickly as possible in my 15 minutes, but this might be a little bit longer than that. So it's a longer paper, but I will.
It's okay, Marta. I think you can just, if you need a few more minutes longer, that's fine. Yeah.
Oh, no,
I'll
just gonna do my little stopwatch. Okay, so my presentation today is "Don't Let the Foxes Guard the Henhouse: Explainable AI as Mask for Cosmetic Compliance." And what this presentation is designed to do is to just provide a few use cases so that you can see that, you know, these claims of this, of the notion that, you know, with more regulations, there will be a stifling of innovation, a stifling of business. Those need to be countered in a counter narrative by the reality of what occurs when regulation is absent. And what occurs when regulation is absent is self-policing and self-regulation. And empirically, and history has taught us that that is not effective. So I'm just going to give you a few examples from a few key companies that you'll be able to hone in on and in conjunction with the existing law, you'll be able to kind of develop a stronger, I would hope, sense of scrutiny and skepticism to some of the public statements, as well as the technical research papers that are being published as peer reviewed. Okay, so first, I just want to give you a little background. And, I just want to like highlight the difference here between, I guess the inherent.
I'm sorry to interrupt you. Do you mind to put your slide in the presentation mode, if you can?
Sure, I can.
Thank you so much.
I won't be able to navigate as well, but sure. Okay. So I was going to jump around a little bit, but okay.
Oh, you want to jump? That's fine. I think we can see
Okay,
that.
there we go. That's fine. I can do it. I can navigate well enough. Okay. So moving right back to, okay, here we go. So here I'm talking about just this kind of juxtaposing these different normative values. And when we're talking about, corporate interests, which I understand they're important, and, we all live in the practical world, but this is just a quote from Sundar Pichai. He's the CEO of Alphabet Inc., which is the parent company of Google. I know you know. And he says that AI is one of the most profound things we're working on as humanity. It's more profound than fire or electricity. And what I would say is that also comes with a price tag. And the price tag is not only in increasing revenues and shares, but it's a price tag that we as a society feel on a multitude of levels. And so I bring up a case by Justice Brandeis, and he says, we must make our choice. We may have democracy or we may have wealth concentrated in the hands of a few, but we cannot have both. And, this is a theme that is continuing to play out. And for some reason, it is this sense that AI has these superhuman, capacities in conjunction with the notion that AI is just bringing us all of these benefits. And that understanding of the benefits that AI is bringing us is not being, circumscribed by all of the negative aspects of this form of technology continuing to be deployed in the market without expertise regulators checking it and ensuring that it is what it says it is. So I first am going to talk about there's so many, the law is very difficult. It's very complex as y'all's world is also, but there's a lot of public disclosure. It's just difficult to find. So this is the Silicon Integration Initiative, and you'll see all of the big key players there. And if you watch the Federal Register, anytime you see this entity at play, you know that something is going on. So this is just a quick example of what occurs when AI is not regulated in this context of this sense of optimism. And what we'll see, I'm sure you may remember this, is the chatbot Tay from Microsoft. And you'll see that, in less than one day, based on her interactions with users, she ends up saying these types of tweets where, Hitler did nothing wrong. Okay, Jews did 9/11. And what's important about this example is, only a few days later, you'll see that the CEO of Microsoft is talking about, what a disappointment this was, that there just was an oversight. And they said it was a critical oversight without really detailing what that critical oversight was. But then within a few days later, the technology is released again, and it's doing the same thing. And, the CEO of Microsoft, what he's saying here also is that it's this sense of heightened optimism that, it's okay, we're just going to keep pushing, we're going to figure it out, without having that calm moment of reflection to ascertain whether the technology is actually ready. And so I'm going to get there we go. All right. So we all are familiar with the big data environment and the amount of personal information that's floating around, whether it's, been de-identified or not. And I just wanted to bring to your attention the sheer content of what is collected. And this is a lawsuit that Google is defending in a motion to dismiss, where it's saying that, look, our privacy policy said we collect everything. So it's just written for you. So therefore, you're on notice of the magnitude and the extent of data that we're collecting at each interaction with one of us or any of our entities or third-party providers. So just to briefly touch on, these are some of the major privacy legislation that we have in place. And then this is so you've got the Fair Credit Reporting Act, the Fair Trade Commission Act, and that's kind of that anti-deceptive provision that you always hear about the FTC going under. You've got the FTC safeguards rules. This is a backup for HIPAA's breach notification rules. Then we've got the Equal Opportunity Act, the Home Mortgage Disclosure Act. There's a wealth of them. I won't belabor it, but these are all privacy laws that have to be complied with. And although there is no overarching federal privacy, scheme, these laws do fill in many of the gaps. But I'm sure, as you all are more familiar with, one of our strongest privacy laws comes out of HIPAA. But HIPAA, even despite amendments under HITAC in the Omnibus Rule, under the privacy and security rules and its de-identification processes, and the manner in which de-identification is prescribed, is still resident with its date of its enactment in 1996. So this is just a quick scheme that I put together about when you're thinking about AI, machine learning technology, like what are all of these entities that are interacting and what kind of sources of information do they need to be cognizant of? And it's a lot. And it also takes a certain level of expertise that a lot of regulators are without. So when we talk about explainable AI, there's many different definitions of it. There's also many different published studies and findings about what explainable AI will take the form of. And what I would say is that, explainable AI and that notion of explainability does have a parallel, not parallel, maybe a parallel meaning and interpretation in the law. The way that these terms are being used, and I can say in my experience with my school, as well as just in the field, by this machine learning community, is distinct from law, and I think most of all the other social sciences. But it's also like a closed form. So even though the machine learning community and their conferences are kind of becoming more open to multidisciplinary scholars, there's still a reticence. And that reticence is also in that these normative underpinnings of law are thought to be able to be tackled or solved through numerical and mathematical computations, which is false. It is helpful, but it is false. So I do want to get to a few of my use cases, but one of the problems and one of the most important things that I believe is kind of, at the base of the issues with explainability or interpretability or intelligibility or transparency is really coming back to the philosophy of science and the epistemology of what knowledge means, and the way that the machine learning community undertakes to ascertain what the scientific method is. What is a hypothesis? Whether prediction and inference require causation, and causal means for explanation. And what I'll tell you is that, and there is a divide between what's a machine learning hypothesis and a hypothesis in the other disciplines of science. And it's also in the scientific method for which those hypotheses are formed. And that really comes down to induction, deduction, abduction, and retroductive abduction. And you'll see that the machine learning community is a part of them are certainly fall within the category of abduction and retroductive abduction. So I did want to get to a few use cases. I'll go very quickly, but my first use case is Google's comments to NIST, National Institution of Standard Setting. And President Trump in 2019 had promulgated a presidential order that required for NIST to come up with basically a federal executive plan about how AI regulation should work. And in that vein, what they did is they solicited comments, this is part of the process, request for information. And in response, the large tech companies came back and provided information. And what you'll see there is that and this is kind of the purpose of that info diagram of where we're looking at all the different sources of information that are required to really analyze and evaluate AI and AI technology. So if you look at the comments that were received by NIST, you'll see that Google is taking the position that because of basically the limits of human cognition, as well as the inscrutable nature of deep neural networks and artificial intelligence, that really you can't really require transparency and interpretability if that's what is going to be required by explainability. It has to be more of a notion intertwined with like a local explanation of a counterfactual explanation instead of a global explanation. And concurrently, while they are making these comments to a governmental body, they're also patenting technology that is a human in the loop method for training a predictive model that increases transparency and trustworthiness. So this is basically a model that is in direct contravention to the statement that, basically there are limits to human cognition as to what can be interpretable within this frame of deep neural network. And then in addition, this trustworthiness for model users and being able to have that sense of interpretability and transparency, and what would deem to be able for you to have an explanation is important, such that I will actually take the time and spend the money and do the efforts to have it patented technology. So, and another thing, and I'll wrap with this example. We don't have the time to do the rest of them, but I'm sure you all are familiar with, the changes to electronic health records, where now most of our health records are electronic, and then they're exchanged in a health information exchange through standardized procedures that are published by advisory body to the Department of Health and Human Services. And the concern comes is when we think about HIPAA and we think about de-identification under HIPAA's privacy rule, and just the categories of information that have to be removed in order for that threshold to be satisfied, then we're still only talking about covered entities. And covered entities are a very it's a much smaller subset of the universe when compared to the value that even de-identified information has, even both before and after its subsequent re-identification. And then when we're thinking about this, de-identified data that later can be triangulated and re-identified as secondary information, you have to consider the level of consent that the actual data subject has provided. And then you also have to think about, moving along, what that form of harm can be for a privacy violation once re-identified. And when we see all of these headlines of these large entities who are now coming into the healthcare sphere, especially when you think about the richness of that personal data that those electronic health records possess and that they take on, you start to see some of the real tangible concerns of why bias is such an important issue in AI and ML, which dovetails with how important explainability and interpretability is. Because if there's no way to check a technology and to verify not only that it is what it says it is, but when you have when you have an acceptance of this, I as a model developer cannot tell you what happens between input and output, and you are trying to contest a decision or otherwise believe it's unfair as a data subject, or otherwise as a regulator are charged with overseeing that technology to ensure that it is consistent, at least with the public's interest and our laws, and not only normative concerns. If that's the accepted ground truth, okay, we'll call it that, then then we're essentially unable to regulate this technology, because the only thing that you'll be able to regulate is whether the process was reliable and produces accurate results. But with the inherent flexibility between what occurs in input and output, and having no check to even decipher or even analyze what that process is, regulators as well as the law will be held at basically in a standoff with the regulated entity, who ends up serving as a co-regulator. And this was just the follow-up example for when we're talking about EHR, electronic health records, and what those mean. We have, like, that's ongoing, and this would get to my third example with Blue Cross Blue Shield. We have this technology that's being employed on data that has been proven to be laden with bias and forms of discrimination. And that discrimination, the discrimination comes from the fact that an AI model is only as good as the data that it receives. And so when you have inherent problems in the data and you have no ability to check, then how does this continued problem that has been studied and has been found, how does that ever really become addressed? And it's not through synthetic data that replicates the same sort of problem. So in wrapping, we won't get through the rest, but if anyone wants to hear about the other two use cases, I will be happy to tell you. In summary, I think that this field, and especially the machine learning community, as well as any of the biomedical fields, when they're ascertaining whether to even use this form of technology in their own research, there needs to be an analysis that is documented and completed that shows that some of these issues have been looked at. And if you think about transparency and interpretability, what you'll see is that and you integrate that with your own understanding of what an explanation means and that notion of causality, then I think that we're all going to come to a closer fitting for a sphere in which this technology can operate and not cause unforeseen, and I would say foreseen, harm. So my brief presentation, but I thank y'all. And if you have any questions, let me know. I'm out of time, but we'll get to those other use cases at some other point. But hopefully that was a good overview.
Yeah, thank you very much. That's really exciting. Actually, no, after I hear your talk, I'm speechless. I'm just thinking so many things we should concern about. We do have a few minutes to answer questions. Are there any questions from audience? You can either, just unmute here and ask question directly, or you can tap it in the chat room. So I can ask you one question first. That's in my mind, because Chris and me, we are working on a project. We try to gather the data, hopefully it's unbiased data from the clinic setup. And then we also combine with the patient history and examination data, try to give the doctor, we hope, right, that our AI tool can give unbiased guidance. But that, really lead to a problem, as you mentioned, right? The data, how we can avoid, any kind of, I even don't know how to phrase it, right? Because when we give doctor we can only give them the data, right? We cannot give them the fact, say, hey, you have to use certain dosage for such patient. Eventually, will be the doctor to use our data to support or to assist her or his decision making. So, are there any cases like that? How we will solve that problem, and especially if in the hospital they will think about the legal issue behind it, right? Because you rely on the data from the research or from some kind of new technology. You don't know what's going on there, right? They just come out with some kind of algorithm, then they give you some kind of score. And then if you make a decision, how you can protect yourself, and then more importantly, how can you really protect the patients? Well,
I think that those, I mean, moving along, I've got a few slides on that, but yes, all of those issues, I mean, it's not an easy analysis, but it's that those are the questions that when I'm talking about the business judgment rule, or I don't know if I got that far, but the business judgment rule, and which is what a corporate board is required to look at. It's also at the hospital level and the executive level. So when you're purchasing technology or otherwise, if you're even training your model on a data set, and it's more difficult when you have an off the shelf version. But I would say as a purchaser, there's a set of questions that can be asked, and even coming down to the training level and what data was used, as well as what mitigation techniques were used in order to kind of deal with the certain biases that we're seeing with the under collection of minority data, the change in medical practices, as well as medical I would say patient populations over time, and how that change in even the volume of data has an impact on whatever technology you're running and whatever decision you're making. So when you have an ADM, even as an assistant tool with a clinician's judgment, there are a set of guidelines and questions that we didn't get to it, but even that the AMA has provided that says, look, these are the things that you need to ask at least at the base in order to ascertain whether you can or cannot even delegate or defer in any sense to this technology. And without doing that, I don't think you have any protection.
Wow. I think we can have. I may have more questions, but I will push it later. Are there any audience, any other people to want to ask some question here? If not, I think we can move to the next speaker. Thank you very much, Marilyn. It's a really nice, impressive talk.
No, I appreciate y'all having me. Sorry, we usually speak for an hour in my world, so I was trying
That's okay. I mean, you are doing great. We have time after all the talks, and we can go back to some discussion. You can show us some more cases, you have in your slides. Thank you.
Yeah, we'll see everyone if y'all want that, sure, no problem. Yeah. Thanks, y'all. I appreciate it.
Thank you. Yes. Stay tuned. So let's have our next speaker. Yeah. So, Chris, are you here? So,
which Chris?
Yeah, let me see. Our next speaker should be Chris Orgonas.
Yeah.
Okay, good.
Yeah.
Yeah, we got Chris and Chris Orgonas. So,
okay.
Just to be clear. Yeah, that's
Chris Orgonas. Yeah, I'm sorry. Yeah. So do you mind to share your? I think you can share your screen now. Yeah, and we can hear you. No problem. Yeah.
Okay.
So I think Chris Orgonas will talk about the med sensor, the medication monitoring using neural network on smartwatch. That's really interesting. Yeah.
Right. Can we all see my screen?
Yes. So you can put it on the presentation mode, so it will be
okay
easier for us to see that. Yeah.
Right. So my name is Chris Orgonas, and I'm a PhD candidate at USC, and I'm gonna spend some time on looking at what you're doing with the sensors, and specifically smartwatches, in detecting human emotions and recognizing human emotions. I need to mention that I have some industry background. I've been a software developer for over 10 years. I worked with banks, government, and I also did some stuff by myself. So without much ado, I'll move straight to my slides. So the background to what you're doing is that there is so much to do with the medication taken that is costing human beings or people in terms of lives, or in terms of compromised treatment or medical complications that some of them even lead to death. And again, tied to this is just loss of a lot of money out of medicine not taken, or more expensive treatment procedures. So I was just checking some statistics of how many Americans die on the road every year, and so that's about 38,000 people lose their lives on the road. And if you look at the number of people who lose their lives due to poor medication or lack of adherence to proper medication, is about 125,000 deaths per year. So it's almost like, you know, you are more unsafe with your medicine on the counter at home than you are on the road driving next to some huge trucks there. But this just, you know, some interesting statistics. But the whole idea is that a lot of people get medicine from the doctor, end up using it poorly, or they don't complete their medication, or somehow they end up in a routine that is not prescribed by the doctors. So as a result, they complicate their medication. And this has led to 3% of treatment failures, 125,000 deaths, and up to 25% hospitalizations. Typically, adherence rates should be 80% or more for optimal efficacy, but that is not the case. It's estimated that the adherence to chronic medication is around 50%. So that's really, really very low. And that is statistics from uspharmacies.com as by 2018. Now, so the aims and objectives of what we're trying to do is develop a medication adherence intervention to be tested among people with one or more chronic health conditions. And we are trying to examine the feasibility and complexity of detecting medication-taking gestures using smartwatches, which pretty much are available in the hands of many people today and very much affordable. So, and they come for very many uses. People are buying smartwatches for sports, for checking their blood sugar, their heart rate, and so many other uses. So at the same time, these watches happen to be laden with a number of sensors, which are very useful for, you know, just studying human motions. The other aim is to develop an AI neural network that can reliably, that is up to 80% plus, detect medication-taking gestures using accelerometer data from smartwatches. So what are we doing with this? We collect data and annotate that data using smartwatches. We got an application and we're using Android smartwatches. So the participants wear the watches on their right wrists, and the users simulate medication-taking activities by a protocol and also by a natural way of doing the activity. By protocol here, we mean that we designed a way of taking medication, which is pretty much the way you take medication, where you open a bottle, dispense medicine, take to the mouth, and then take some water and drink, and then lower the cup back to the table. The entire time the watch accelerometer sensor data, or other sensor is recording, we're logging that data to be able to understand, you know, what are the motions in terms of the XYZ values in that sensor, which are recorded. And this is what we pass eventually over to the machine learning for training. So we pre-process that data of the raw orientation accelerometer sensor data to make it input ready for neural network training. And then we train the neural network to generate reliable models that can detect medication gestures. And then we basically go ahead and look at that data in terms of, we analyze the data to look at the performance, if we've been able to meet the expected performance. We conducted different experiments, investigations, in order to be able to develop the model we're talking about. So we explored the capabilities of the network when trained and tested with protocol-guided data from all participants. The test data was 20% in sample dataset, the protocol-guided dataset. We explored the capabilities of the network when trained with the protocol data, guided data from N-1 participants to be tested with the nth participant. This is the case where we basically, the data we used for testing was not part of the data we used for the training. So it was purely foreign to the model. And then the preliminary exploration of training network using all gestures. That means that both the protocol guided and natural data from N-1 participants and tested on the nth participant. Again, the natural medication gestures is basically, we tell a participant that just go about taking medicine the way you take medicine. Forget about the protocol we designed for you. So they would be able to do 5 medication gestures per day for protocol and for the first 5 days, and then do the next 5 days for natural gestures. So essentially, the whole idea was that if we had them to do the natural gestures and then do the protocol gestures, then they would not be influenced by the protocol gestures in doing the medication gestures. So ideally, we looked at just how do people take medicine? These are pill medicine without getting influenced by the protocol we designed for them. And so we take those gestures, and that is part of the data we use for the training. At the same time, we had the protocol data, which is which is what we have here. I just explained. So basically, the protocol medication gesture is where you wear the watch on the right hand, and we have an app which is running on the smartphone. So you start that process. You open the bottle with the right hand, dispense the medicine from the bottle in the left hand onto the right hand, then take the pill to the mouth using the right hand. Pick up the water and drink using the right hand, and then you stop the medication. The reason we're doing the start and the stop medication is because this is helping us in doing in automating the annotation process. So if we run this through another program, we're able to pull out the medication gestures of interest instead of just going to do this manually one by one, because it's a lot of data. If you look at 3,100 gestures. So if we do this start and stop, then we're able to identify easily the data of interest or the sections of the medication that we care about. Now, if you look at that slide, this is a sample medication gesture. And if you look at that data, before you plot it, it's just, XYZ values. But once you plot it and then get to look at what happens. Now, the section A is where you open the bottle, and it begins around here, and it goes all the way to the end of A. And then the section B is where you do the hand to mouth, pill to mouth, and hand off mouth. So this happens pretty fast in most cases. So you toss the pill to the mouth, and again you go back to reach out to the water. So part C is where you pick up the water and drink the water and lower the cup to the table, and then you close the bottle. So we can dissect this further, but because the whole idea of this is to be able to characterize the medication gesture and be able to allow the model to recognize, okay, what comprises medication. So if you look at the hand to mouth in drinking water or in eating or in smoking, you're going to see a very similar pattern in all those scenarios we dealt with. So you can be able to, the main thing is to recognize these subsections in some order, so that we know that you don't take medicine before you open the bottle. So if they come in that sequence whereby you open the bottle, dispense medicine, medicine to the mouth, then grab the water, drink the water, close the bottle. Now, if that's what happens in that order, then the model will recognize a medication gesture has taken place. So, so this is basically the gesture, and they're not exactly the same, but when you look at them, you're going to see a pattern. And this is what, obviously, if you pass thousands of them on the training in the machine learning, then the model gets to understand, okay, this is medication. And again, there's a variation, of course, if you look at it from person to person. Some people take it much faster, some slower, and some may open the bottle a little different. But the whole idea is that if we're able to expose all these to the model is able to understand and recognize that, okay, these are medication gestures. And so when you test and it's able to detect exactly what, is this medication or not medication? Is this eating or not eating? Then that is the whole goal, the whole point. Now, so with that training, we were able to obtain some results in sample accuracy of 98.5%, which is pretty good for being able to detect medication. And then there was the out of sample. The out sample, remember we said that is why you try to generalize with a foreign data set that was not part of the training. The in sample, we basically tested with a partition of a sample that was part of the training. So then of course that was the protocol data. Protocol data is where it was pretty much straightforward. We were using a certain way of taking medicine, so everybody knew what to do, and that was clear. And then there was the protocol and the natural data. This way you combine the natural way of taking medicine without any influence of any protocols, and then you brought in the protocol and the natural data. And then the in-sample accuracy was 95%, which is still impressive if you look at the fact that people were able to bring in their own manners of taking medicine without any undue influence on how to take medicine. And then there's the out sample. Now the out sample accuracy of 87% is a little lower, but I think it's a better picture of how the model would generalize in most scenarios, because this way you bring a whole foreign data set, which includes the protocol and the natural gestures, and then expose this to the model that was trained on the protocol and the natural medication gestures. And then you're able to obtain 7%. If you look at the beginning where we said that the goal was to obtain 80%. So that means that even with the natural medication process, we're still able to hit the target. We're doing more studies on this. We're looking at this data as a time series data, and also applying LSTMs, and we're seeing more interesting results. In this case, we use conventional neural network, and even with this, we're still able to obtain the target numbers. Of course, if you look at the way we're doing annotation, there's more to be done, because if we automate the annotation process of these gestures, as you realize, if you look at this gesture here, you notice that in the section A, there's a bit of it which is, kind of flat. If you look at the beginning of that, you notice there's a flat section. That is data that is not part of the gesture. It's just before you begin. But if we do the annotation, automated annotation, then you realize that we somehow to include some noise, which is not really part of it. So we do the estimation maybe to move a little bit into the gesture, to be able to chop off that preamble part of it. You go to the end of the section D. Again, that is pretty much you're done with the medication. You close the bottle. So the sensors are just not doing much. I mean, the watch is lying, maybe your hands are lying somewhere, not doing anything. So the disadvantage of doing this automated annotation is that you carry with you some piece of unwanted data. So still requires you to do further, approximation of, moving inwards into the gesture you have, or having a human being still having to look at the gestures and do further cleanup. And we've done some cleanup in the current study we are doing, and we're seeing that's making a difference in terms of the correctness or the integrity of the gestures we're dealing with. So that's part of the ongoing work. And obviously, this being an exercise that people have different ways of handling. We have unique medication gestures where every person pretty much has a signature on how they do things. I say some people are fast, some people are slow, and some people do those activities differently. Nevertheless, the whole idea is to get a pattern, and that pattern is what the model gets to figure out. So based on one above, no one model fits all. With necessary hyperparameter configurations, it was possible to train models to recognize unique aspects of medication patterns of different persons. It was a challenge where persons engage more of the hand without the smartwatch, hence leaving out crucial hand motions from being captured and then detected by the generalized models trained on more common gestures. Now, there's situations whereby there are persons whose natural medication gestures involve maybe using the left hand more than the right hand. So if you have the watch one on the right hand, then it means that more activities that is of interest is kept, or rather is being unnoticed because it's happening on the left hand, and so you actually don't detect medication in some of the cases until maybe you realize, okay, maybe how many left-hand persons did we have doing natural gestures with a watch on the right hand? So that may mean that you do some training with watches on both hands, but again, that's not the way people wear watches typically. So we have to look at some of the scenarios carefully and think on how to be able to get information from the hand that is doing the medication. The models trained in both protocol and normal gestures data produce more realistic picture of real-life gesture recognition. Yeah, I just mentioned that the 87% here is more a better picture of how this would generalize in real life. We're actually doing the work of being able to port this over now to regular watches and just have it people use it, like go about your life, and if you're taking medication, you need to be reminded, or you need to be alerted if it's your time for taking medicine, or if you forgot, then it should be a way for you to be able to get that information. So there's more that can be built out of this intelligence. You can do reminders, you can do alerts, and the whole idea is to help people be able to take medicine correctly, and that can help them avoid all these treatment complications about medication. So we use a range of tools here. We use TensorFlow, Keras, of course, Python in this, and smaller tools like Excel. And we develop most of the code here in Google Colab and Google Collaboratory. Yeah. And again, I acknowledge the Econ team of College of Nursing, and of course, Valafar Lab team at USC. If there are any questions, I'd be glad to answer them at this point.
Thank you very much. Yeah, it's a really nice talk. We have a question from the audience, from Shan Qiao, asking, how about the influence from the gender and the age of the participants?
You mean the influence of?
Yeah, will the gender and the age of the participants influence the results?
No, that remains to be seen. So far, this is the experiments and the tests have been done using pretty much young people who are students. This is going to be targeting maybe elderly persons. So when we run tests on elderly persons, again, I think we are bound to see different results because the speed of taking medicine may be different, they may be slow. For now, it's done by mostly young people who are, college level, and so I think their ability to move, to have sharp motions and get things done pretty fast is very much a feature of this data. Again, I cannot answer that really for sure because we haven't tested this on very old people or very, very young people.
Thank you very much. I think we'll have another question from Flory. Maybe you can unmute yourself and ask a question directly.
Yes, so I was wondering, I'm coming from Europe and being a part of the diversity here. So we bottles with medication in there that can cause great harm if you take larger doses than prescribed are forbidden here. So what we have is blisters, this here, So this would then be a totally totally different picture, I guess, because we are instructed to take out a pill like that, which is very different. And then mostly we have to, I don't know whether you can see it in the camera, it is perforated. So we take like half of the pill or so, and we have to adjust our dosage this way. This would then be a totally different picture. Just has it been tested on that as well so far? Are there any results?
Well, I did not see the demo you just did. I don't know if somebody was able to see the picture.
Okay.
It's like what we have here when we take antibiotics. You know, there's like there's a certain sequence of pills you take, you know, for so many days, and they're sort of labeled.
Okay, so so you're asking if we've been able to test this on a different type of bottle, other than the one
we don't have bottles at all.
It's not a bottle. It's just something. You know, if you ever have some medicine, they just I don't know how to do that. You know,
pill pack.
Yeah, pack.
Oh, yeah, I can see what you're talking about.
Yes. If you look at my screen, I don't know whether anybody can see it.
I cannot see your screen. I can see your screen.
Okay. Yes.
Yeah.
So we have those blisters, on which you would then push one pill out like that. You would take it out and then break it in half to get your dosage. So which is a completely different accelerometry pattern that you would then have in the data. I was just wondering because bottles are not allowed here. So
yeah, I know we haven't tested that, but what I want to mention is that there are even here in the US, there are very many different medicine containers. Even the one that you pop, that is not really, we haven't tested that because it's going to obviously give us different gestures when a pop is going to be showing me something different. So I'll look at this like more of a proof of concept study, whereby, if we're able to actually take up a study and run it to the end and be able to recognize medication taken properly, then we can do the same on pop. It just means that there are many scenarios we have to put in mind when talking about medication taking process, and you might want to look at what is common, and then maybe target that as well.
Of course,
but
yes,
obviously, once you pop those kind of whatever, then the rest begin to look the same. So it might be also one of the things we're looking at also is okay, what are the sub activities, and okay, if I combine sub activities from scenario A and B, do they make a recognizable activity? So maybe if I'm able to see that there's hand to mouth, followed by water and stuff like that, then I might want to begin to look at what else happened. Then if you put all that together, then it can add up to a recognizable activity, which can be medication or eating or smoking or something else.
I wonder how personalized those actions are. The suggestion here is that you could sort of broadly, you have an algorithm that's sort of broadly available to use the training data from a large population, and it becomes more accurate. But I wonder, couldn't you just get by with like overfitting a neural network to one person's actions? Like sit them down, in the doctor's office, have them go through 10 motions, use 20 motions, train your neural network per person, and then just predict it for them. It's their neural network that classifies their actions. Because I can imagine that it's so sort of, there are probably a series of sequence events you have to sort of fish out the pill from the bottle, et cetera, et cetera. But I can imagine that it's very personalized.
Yes, it's personalized and it's a signature. That's why we call it a signature, because the way you do it is not even the way that your brother or your friend or your spouse does it. Even yourself, you don't do the same motion twice, exactly the same. So the good thing about machine learning or develop these models is that they're not looking for exact, really, you don't have to reproduce exact signature like, John and James doing the same thing. But they're able to generalize, whereby, that's why we can train in the lab environment, but once we deploy, is able to generalize for different persons. So you can train for one person in the doctor's room, but if you make it very specific, you're going to run the risk of trying to run the same for everyone. Because
that's what I'm suggesting. You train a light model per person, for example. I wonder what your accuracy would be, because you saw that the out of the training data sample of the population that's outside of your initial data set was 87%.
Yeah. Correct.
And so I wonder if you could achieve a higher accuracy if it's just a very overfit individual-based model that you average the accuracies across, say, the 31 or the 10 participants you had for your data, or 31 participants, and then see if you just essentially take a average accuracy across each person. If you could get something better, like it doesn't really matter, right? You could overfit the data if you have a watch that
yeah,
you could use to generate the training data.
Yeah, that sounds interesting. I just imagine that you're doing this for a whole range of people, and you're going to have quite some data to deal with. But that's a good point. I mean, I agree with you. That would be very specific because you're now producing, the very signature of, the person whose data you're training. But the goal, of course, is to see how you can train on a data set and be able to generalize a lot easily for a population.
But why? Why would that be the goal? Would be just to sort of identify if they take the pill or not, right? I mean, if the goal is just to sort of, if you want to remind somebody to do it, then you just why not succumb to overfitting per person? Why have a generalizable model?
So no, the point is, so assume that I have an app on Apple Store or whatever, Google Store, and I want to download that app into your watch, and I tell you, okay, go about your life. If you're taking medicine, just have this active so that gonna check for you. So basically, the consumer is gonna just download the app and have it run in their watches. They're not gonna have a further training on that application. It's just gonna.
You can have a countdown. You can have them sit down, and count and have a count of 20 or whatever, and have them simulate 20 times individually when they download the app to take the pill, and then that becomes the training data.
So are you suggesting that after somebody gets an app from the App Store, they begin to train themselves on how to take medicine?
Yeah. One model, one person.
Now. So I'm gonna put my life.
Sorry, I have to cut in here because due to time issue, we still have time after our talks to have another 20-30 minutes discussion time. But now I want to keep in schedule. So let's thank Chris O'Connor for the nice talk.
Well, thanks, Chris. Thanks, Namesake. I think we'll explore that later.
Yeah, we can talk that later. Yeah, and maybe we can welcome our next speaker, Siyu. If you don't mind, can you stop sharing your content here?
Sure.
Chris,
there you go.
Thank you. And so you can put your content in. Thank you.
Can you hear me?
Yes, we can hear you, and then you can put your PowerPoint on PDF. Yeah.
Make it So hello everyone. So I'm a PhD candidate from the USC Biostatistics. So today I will talk about the topic which is called the false discovery rate control for the lesion symptom mapping with the heterogeneous data via the weighted p-values. So I will talk about in 3 parts: the background, the methods, and the neuroimaging data analysis. So first, let's talk about what is the voxel-based symptom mapping. So the video that blocks it. Okay. So the lesion symptom mapping aims to find the relation between the behavioral or the cognitive functions and the regions of the brain among those patients with a brain injury, such as stroke. So the voxel-based lesion symptom mapping is a type of such task that relies on the structural MRI image to find such relations. So the VLSM relates the lesion structure in the MRI images and to the cognitive functions. So in the images, they are measured on the parcellated 3-dimensional voxels, which each one is a 1 cubic millimeter. And given there will be a hypothesis test in each voxel, the VLSM analysis can be regarded as a multiple hypothesis testing. So the voxels have the following two properties. The first one is an unequally distributed lesion may cause a heterogeneous power among the voxels. So, and the second one is there are spatial dependence among the voxels in the brain. And it's a weak dependence, which means that the p-values correlated within the regions of the voxels and nearly independent across the distant regions. And then the hypothesis test on the voxels, they should have the same properties. That's what we need to solve that by our method. In this topic, there is another important term, which is called the false discovery rate, which need to be controlled in the analysis. And we can see in this table, so the M is the number of the total number of the tests, and the R is the number of the significant test result, which we can also call it discoveries, and V is the false discoveries number, and S is the true discoveries number. So FDR is actually the expected false significant test proportions when there are at least one significant test result, and we can calculate it through the V divided by R and through this formula. Another important term is called the expected number of true discoveries. It's called the ETP, the expected number of the S, which is what we need to maximize in our method. So it can also be expressed as the sum of the prior probability of the non-null and multiplied by the power function of each test. So some common FDR control methods include the BH procedure, adaptive BH procedure, and the 10% rule method. And here the 10% rule is actually the BH method on the voxels with a damage proportion greater than 10% and less than 19%. The commonly used multiple hypothesis testing method may less likely to detect the significant hypothesis for the data in the VLSM study. So as our goal is to find more significant hypothesis tests under the control of the FDR, so we propose a weighted adaptive BH method, which we use the weights on the p-values to focus on the test with a high power in order to find more significant hypotheses. So remember, we have the weak dependence in the analysis. So to deal with this, we can control the FDR asymptotically by applying the ABH method to the weighted p-values under the weak dependence situation in the VLSM analysis. So the first thing we need to do is to calculate the weighted p-values, which is the QM, which divided by the p-values, divide the p-values by the weights. So the key point is that how to estimate the optimal weights for each test. Then the first step is to estimate the power of each test. We derive this formula, and we can see that T is a threshold, and the eta M in this formula is called effect size, and we'll talk about this later. And the SM is a predictive standard error, which can be calculated by the formula, this formula. And we can see that XM average is a proportion of the voxel lesions among all samples for each hypothesis test or the voxels. So the RM squared is a coefficient of the determination for the linear regression. So the outcome on the lesion size, it won't change much for the different tests. So it's like the similar thing. And after we got the power function, we will just plug that in this optimization problem. So here we can see that in the max function, it's actually the ETP. And after that, the control criteria is a controlled FDR as the alpha, which is generally as a 0.05. So we will solve this optimization problem by the Lagrange multipliers, lambda. After we got the estimated lambda, we can just put it in the threshold function and calculate the optimal ways. It's just that the threshold for each test divided by the mean of the threshold through all the tests. So here the TM is the threshold for the test, and the PM here is the estimated prior probability that the hypothesis is null. So as I said in the previous slide, that the effect size is a eta m is important. We need to select the best eta m here. So in our method, we set all the eta m equals to a fixed value, which is eta. And we got a plot, which is weights by the predicted standard error, SM. So the larger the predicted standard error, the smaller the power of the test. So we can see that if the value eta is too small, which is like the eta equals to 0.1 or less than that, so most of the weights which are greater than 1 are focused on a small number of tests with a high power, which is a small predicted standard error. So this may cause a large amount of tests without the high power, or they may be heavily downweighted. So if the value eta is too large, such as 0.25 or the larger, you can see the black dash line. So it still may cause the test with high powers being downweighted. So we need to find a best eta value, which is why we propose an MW criteria to find the maximum eta value when the weights start increasing by the increasing of the predicted standard error. So in this plot, we can see that the black solid line, which is the best, we found MMW eta value, which is 0.178. We can also calculate this MMW effect size through this formula. Here, the S1 is the smallest predicted standard error among all the tests. And the formula for the C lambda, we can see the P, that is a test statistic for the prior non-null probability of all the tests, which is such as the mean of the P or the maximum value. And then we applied our method to a real data, a neuroimaging data. So our sample include 220 adults with a chronic left hemisphere stroke and aphasia. So for each person, the lesion was mapped as a binomial volume with a resolution of this size, and according to their MRI images. So it's like for each person, and for each voxel, they'll have the lesion status like 0 or 1. And there are totally 834,582 voxels with the damage to at least 1 person. And for each voxel, we'll fit a logistic regression model for that. So here in this model, we will see that XIM is whether for the person I and the voxel M has a lesion or not. If this is 1, it has a lesion. So, and the Y here is called the official quotient score for each person. It's a logic transformation. So this is about the severity of the language impairment. So an X plus is the total lesion size, and it can be calculated through the following formula. So it's more like that for person I except the voxel M. So what proportion of the lesion this person may have. And after that, we then applied in the following file method to the test statistic. And here in this model, we'll see that alpha 1m. You test whether this alpha 1m equals to 0 or not to test whether they have a relationship. So we'll got the p-values and some related test statistics, and applying this file method to those test statistics, and we will find these results. There are three parts. The first part is the proportion of the inconclusive test. So it means that as we have the weights, the test is viewed as inconclusive if its weight is less than 0.1. And we have the maximum weight and number of discoveries. So compare the three WABH method with the different eta value, 0.1, 0.25, and 0.178. The 0.178 is estimated from the MMW criteria. We can find the increase of the eta value may result in a small proportion of the inconclusive test and the smaller maximum weights. So the test, let me see. Okay, so we will only find when we saw the number of discoveries, we will only find the discoveries when the eta equals to 0.1 and 0.178. For the other method, they are all 0. So, and then we will compare the MMWWABH method, which is the eta equals to 0.178 to the 10% rule. We'll find that their weights performance are nearly similar, but for the number of discoveries that performance that our method is better. And these two figures are the result from the WABH with the eta equals to 0.1. They have the largest number of discoveries. You can see the top figure shows the weights on the brain image, and the color means that the weights, and the gray part indicate the inconclusive test. And we can see that most of the tests are inconclusive. So the bottom figure is a red. We can see that it indicates the significant test. So the red part indicates the significant test voxels. So we compare the two, we'll find that the significant tests, they mostly have the relatively high dead weights. So among all the significant voxels, so their average weight is 4.56 and the range from the 0.19 to 5. And you can see that 95% voxels have weights greater than 3. So as we can see from the previous result, we can see the larger the eta value, it's smaller the number of discoveries, but it's not always the case. So in general, we will just small eta values should be avoided since they result in the many inconclusive hypotheses. So we propose a novel criteria, which is the MMW criteria for choosing the effect size, which can minimize the impact of the weighting when the study is underpowered. So the impact of the weighting can be varied in our procedure. So the WABH can work well for the multiple hypothesis testing study with the low power and the heterogeneous power. So in the future, we'll study on the situation when the non-null prior probability are different for each test. And these are reference, and that's all. Thank you.
Well, thank you very much, Siyu. So are there any questions to Siyu specifically from the audience? Yeah, so maybe, we can just first, we still have time for the further discussion, but I want to thank all the speakers for the session. And unfortunately, Nina cannot join us because some technical issues. And especially I want to thank, Flore. Are you still here? It's pretty late for you, right? Yeah. Yeah, so he
yes,
joined
it is
us,
actually, indeed.
Yeah, he joined us from Europe, and then he did actual work. Actually, he videotaped his talk just in case there are some technical difficulties. But fortunately, he can make in person. So thank you very much for joining us. I think we still have about 10 to 15 minutes to have a discussion. So any question to Siyu? If not, I think we haven't finished the discussion between Chris and Chrysogonas. So I think Chrysogonas, do you want to have some comment on what Chris said? You can train yourself individually and then just like we do the facial recognition, right? Same idea there, right?
Yes. Can you hear me?
Yes, we can hear you. Yeah.
Okay, good. Yeah, Chris was saying that how about you let each person train their model and so they go about their lives and it's able to recognize if they had medicine or not. Yeah, that's a good perspective. But I was just thinking about so it means that once we have you have an application that is deployable on a device like a watch, then it means that every person who download that application begins to train that application on what is their medication, how they take medicine. Yes, which is still achieving the goal because you can make it recognize that, okay, this is how to take medicine. Yes, we didn't really think for that, but I think it's one of the ways to solve the same problem. Because the bottom line is, are you able to tell yourself that I've had medicine or not? Whether you trained a model that's ready for everyone or you trained a model specific to individual, I think the goal is the same in this case.
Yeah, the goal's the same. It just might be easier. I just wonder how generalized the model accuracy, how accurate the model will be between those two training data, essentially. Because in one case, you have to keep wrapping it back in to the overall data. And I don't know, it just seems, maybe there would be maybe it would slow down at some point. You have too much training data for the neural network.
Yeah, yeah, I think that's a good thing. Was we'll try to compare, maybe do something, some experiments and look at just what approach is better in solving this kind of a problem.
I always had this impression when whenever you get off the plane in the US, and you go through security, and by the time you get to the desk for the Homeland Security, where the Border Patrol, I forget what they're called actually, and they know who you are. They have the screen and already identifies you, and it's a pretty easy modeling task. It's not that they have a good algorithm. It's just an easy modeling task. They already have your passport image, and they have a limited data set, right? So it's a really, they have a high success rate probably. And that's my assumption. I mean, Marilyn might have some comments about transparency of the algorithm. I've never seen the algorithm, but I'm just assuming a lot about it. But I think that's a
good point. I do have one question before I have one more question to Marilyn, if you don't mind. I still Marilyn, I just want to grasp what you talk about. So it seems like there are a few things we have to worry about or think about when we develop the technology here. One is how we can make sure this we call it a dark box like algorithm can give us unbiased data and then can lead to the right can be helpful, not harmful. A second thing I think you worry about the privacy, right? Because in certain situations the AI themselves can maybe penetrate our privacy the data without our knowing. And third one, of course, maybe some big corporation, they can manipulate the data, right? Are there any other thing we should worry about or we should think about while we develop the new AI-based biomedical care?
Well, yes. I do think that the privacy element is very difficult because, you know, in the US we have sort of, you know, it's almost, it's like we accede our autonomy and our sense of self through consent, and it's not a true knowing consent, but it's something that we have, you know, just adopted as the course that we'll take for what will be that fundamental floor for whether a, you know, an entity will be licensed to take and then sell your data. But I think that, you know, definitely in the provider context and certainly in the researcher context, I think another issue with privacy and this sort of, you know, data oligarchy that we're kind of becoming more and more familiar with is when you are researching, you know, if you do have only access to a certain amount of data, how are you able to, you know, access other forms of data? And I think that kind of brings us into an area that academics don't necessarily like to delve into as much, which are really conflicts of interest and disclosures of conflicts of interest, and what that means within your funding, and whether there's a, you know, there should be like a certain almost separated, you know, department, or I don't know how exactly how it would be structured, where those sorts of conflicts are, you know, subdued to a degree in trying to get this sort of funding. Because, you know, I will say that the studies will show that in the machine learning community, if we look at the way that big tech is operated, it also operates in a very similar way to what we've seen with, you know, the asbestos litigation, as well as the tobacco litigation. This isn't like a new strategy. The strategy of, you know, really kind of introducing ambiguity that will then be resolved by conflicted academics who are in some senses on the payroll is something that is not new. But what we're seeing in the machine learning community is that there's a less, I guess, a less of a recognition of it. It's this understanding, an idea that because I'm just using my mathematical model, I'm almost, you know, separated from any sort of influence that I could receive from funding, from a corporate interest, and whether I have to review my findings or not, even if it's under like a overarching view of, well, we're not going to interpose our, you know, policies on your findings. There's still an influence, whether it's implicit or not, about whether you'll get that funding your next year. And that funding is, you know, becoming more and more predominant. I mean, we have a, you know, an AI institute here, and, you know, what level of disclosure will be required for academic papers and publications, I think is something that's we should all be really focused on. You know, there was a 2017 and 2018 article by a group of scholars by the Oxford Institute of Information Technology. That might be not the technical name, but something along those lines. And, you know, each of those scholars had, you know, funding from like the big tech, you know, conglomeration, and they were opining on whether a right to explanation under the GDPR arose or not. Of course, they were opining that it does not arise. And I think those types of like conflicts and disclosures are something that we really need to take very seriously on the academic side. And another very important issue that I would just bring to the light is that is the notion of documenting the analysis that's undertaken in analyzing where your data comes from, what the features are, what you've done in order to kind of, you know, balance those features, what you tried, what you didn't try. And, you know, in the design process, whether it's the experimentation phase or whether it's deployment, you know, these types of decisions have to be documented. And that's something that I know is painful, at least from what I see in my brethren in machine learning. The more you have to write, you know, the more painful it is. Whereas in law, we just keep writing, we can't help it. But it's something that needs to be, I guess, there needs to be a stronger structure. And I think that what the problem is, like, there are so many different structures for different contexts. But if you look at them, you know, there are main principles that you can coalesce from them that anyone, I think, really should be employing in using any form of this technology.
I
from,
think that's the reason why we need someone like you, not only have the background in law, but also you want to dive in such kind of very difficult domain of the research to understand us better, right? Yeah.
well, I think that I think that one of the mishaps that we've encountered is, it's really it's crossing this language barrier. When I use terms, with my graduate level, PhD level classmates in computer science, we're not even talking the same language often, and it's really kind of trying to make sure that you're not just looking at the data and whether the model fits, or whether you're like getting no errors at the end, and you're getting the kind of accuracy you need, but what do those features actually mean in that data? When you actually like dig in, like what is this, like what is this column, like what does this mean? And I think that's one of the things that we're kind of missing, because it's not just like a zip code. That's such a latent thing of so many different things that can be incorporated into that one feature. And what does that mean? And what does that mean for your study and your results? And how are you going to actually mitigate whatever that could bring into the study? And it can't just be through like a NaN or like coming up with a mean and just imputing it.
Definitely. I think Marilyn, your talk really gave us a lot of things to think about it. But when you talk about the how we can really have different language. So I don't know whether you're still here. I really have one question to you, but it's nothing to do with your the analysis part. Is the work you are doing here, you are really working on hard cloud data analysis, but then you have to deal with the data from the clinician, right? The imaging you show us and then some other things. So how easy, when we talk about the communication issue, how easy for you to really convey your message to the collaborators?
So for that data, neural imaging.
Just in general, right? You have this data, you give some kind of conclusion. How easy for you to convince your collaborators, say, hey, that may be something you should consider, or it's really hard for you to find the communication channel to really make sure he or she, the clinician, they can understand your data here.
I think actually that I'm more just digging in the method part, so I didn't encounter just much problem to convey that my conclusion to those people. That
so mainly is maybe your advisor or some others doing that part of the job. You just
I think maybe.
Okay, understand. Yeah, I think that is something for me, as a wet lab research scientist. The data part is always a hard thing for me. Like I have collaboration with Chris, so it's really hard for us to find a common platform we can really know each other. Other than we can drink a beer together, but other than that, it's really hard. I think we have about maybe 1 or 2 minutes before there's another meeting behind us. Chris, do you want to say something?
I have a specific question about the neural network configuration, but it's not a general. It's both to Fleury and to Chris actually about the input layers. You ever use symmetry? I mean, you mentioned this sort of this spherical operation of the hand movement, right? But you guys both sort of seem to be presenting just simply 2-dimensional coordinates or 3-dimensional coordinates, maybe Cartesian coordinates. But do you ever actually sort of try to encode some sort of angular component to it?
Is that mine?
For both of you.
Either one. Like yours specifically was about sort of these 3 dimensions of hand movements, and you can imagine that there might be an angular component too.
Yeah, okay.
Yeah, of course. Gyroscopy is the word here, I think. Yeah. So you have X, Y, Z, and you also have the rotation around the axis, or at least I'm sure Chris is also implementing this.
What's it called? The angular component?
It's not an angular component. Angular is then the combination of 2 axes, but it's called gyroscopy. This is then the rotation around that axis. Okay. Also, what you can implement is the attitude change, which is what you mean in angular component, which is a linear combination of axis information.
Yeah, I was
this
going
is
to say
input,
the same.
or this is done as a mathematical operation on the second layer.
Yeah, the gyroscopy is the rotation around the axis. So that is not, that is an additional sensor data, but also attitude change, it is called, is then a combination of the data of several axes of the change of the position.
So Chris Gonas?
Yeah, actually, pretty much Florian has answered that. We use the gyroscope, but I need to add that the more sensors you fire in the watch, the more energy you suck out. And so you don't have the battery lasting long enough. And pretty much the accuracy you attain by just accelerometer is more or less sufficient than going to use the gyroscope and accelerometer. So, there's the give and take when you fire those many sensors. Again, the watch doesn't have such a good battery if you're going to be lasting long enough in the day with the watch. I
think it's remarkable. This is all sort of encoded. It's all, the sensors are there. That's I didn't realize the sensors were already in the Fitbit. That you're walking around with a gyroscope. It's such a complicated thing that's already contained in your Fitbit. That's amazing.
What we started to implement as well is data sporadically from, if we detect a pattern that somebody is going up the stairs, we are incorporating barometer data. So altimeter, barometric pressure, because this is a sensor that is built in a great many of smartwatches exactly to detect this. So that's a funny side note. So I'm a paraglider and a base jumper, so I actually use this myself and programmed apps based on this. So yeah.
That's a good excuse, Flory. That's a good excuse to go jump off a mountain and do some base jumping for research.
I think I have to end here. We have to end the session. Thank you very much, all the speakers, Flory, Siyu, Marilyn, and Chris Gonas, and also everyone participated in the the conference. And thank you so much for staying here for the 2 hours. And hopefully we can have more interesting discussions tomorrow. And if you still have some comment or questions, we can always use the Hua to input your input. Thank you so much. And then you have a very lovely weekend. The weather will be nice here. I don't know about you, Flory, but enjoy your weekend. Thank you so much.
Thank you.
Bye, everyone.
Bye.
Thank you, Chris.